Okay, so we'll now be looking at part 2 of exam 3. And here we'll be coding out the temperature profiles for that insulated bar that we saw in part 1. And we're going to be using those Craig-Nicholson finite equations in order to solve and then plot. And we're going to start by importing the numerical Python that we need. So I'm going to go ahead and do that. And then we know we'll be plotting, so we're going to be getting our plotly subplots and importing those subplots. Okay, and then we're going to go ahead and import our plotly.io as PIO as always. And here we're going to be getting a linear algebra function. This will be used to import our solve banded function in order to solve the matrix that we'll be making. So from scipy dot linear algebra, we're going to import the solve banded. Alright, and then finally we're going to get our templates and just change the color. To dark. Alright, it looks right. Let's go ahead and move on that and make sure everything goes okay. Still loading. Oh, whoops. Don't know how to do that. There we go. Cool. Alright, next code. We're going to basically set those matrix functions and solve the matrices that we make. So first we're going to need to set the bar length, so nx is going to be equal to 50. That's how long it is. And then we know the time is equal to an hour. So in seconds, which is what we're going to be calculating, it's going to be 3600. Then for our initial temperature, we're going to be setting that equal to our 20 degrees. So 20.0, make sure some decimals. That's how Python likes it. And then for our left boundary, we're going to be setting that equal to 50. That's the temperature that we know. And then we're going to move on to our coefficients that we know. So we know alpha, which is our thermal diffusivity coefficient, and that's given to us as 1. We know delta x, which is also given as 1, and we know delta t as 1. And those are just the step sizes that were given to us. So we're going to go ahead and set our x equal to np.arrange using that nx, which is 50, and then multiplying that by delta x. Then we're going to set our r, which we know as, based on our equation, it's alpha times our delta t, and that's divided by 2 times our delta x squared, which is our position squared. Okay. Now we're going to go ahead and move on to our coefficient matrices. And we know first we need our A coefficient matrix. So we're going to go ahead and set A equal to our np.zeros. And we know it's a tridiagonal function, so we have a top, middle, and bottom position. So it's 3. And then we're going to say nx minus 1, and we know it's minus 1 because you can't reach the right boundary. Okay, so then we're going to set A going from 0 to colon. That's just going to be set equal to -r. We know A from 1 to 48, which is pretty much 47, since you don't count the last one. Actually, first we need to do our colon 48, sorry. And that is going to be set equal to R1 plus 2 times R. Okay. Then we know A from 1 to 48. That is going to be set equal to 1 plus R. And then we know our A from 2 to colon is going to be set equal to R negative R. Okay, so that looks right. So now we can move on to our B coefficient matrix. So we'll just say B is going to be equal to our np.zeros again. But this time we know that our B matrix is only one dimension, so we only need the nx minus 1. Cool. Alright. Now we can move on to plotting our data. So we're going to get our fig equals make subplots function. And then we'll have set rows and columns equal to 1. Okay. We're going to do our fig.add scatter function and set x equal to x. We're going to set y equal to t. And name is going to be set to initial, which you'll see with that initial temperature. Okay, that looks right. Now we're gonna move on to our for loop. So we're gonna need to take the last value into account when doing this for loop. So we're gonna say for I in range of 1 to nt plus 1, taking in that last value. And then for our left boundary equation, we're going to be doing B0 and using that the equations that we made with the Crank-Nicholson, which is R times T0 plus 1 minus 2 times R times T1 plus R times T2. Okay, that looks right. And then for B0, we can rewrite that as B0 plus R times T0. Alright. Cool. Alright, so now we're going to go from B1 to 48. And this is technically 47 because it doesn't count the last one. So we're going to do the same thing, R times T from 1 to 48. We're going to add R1 minus 2 times R. And then multiply RT from 2 to 49. Alright, and then just for our next one, which will just be 48, we're going to set that equal to r times t of 47 plus 1 minus r, and that's going to be multiplied by t of 48. And then, yeah, I think I forgot something in this row. B of 148. Yeah, I think I need to add something. Add the r times t from 3 to that. Yeah. Okay. Alright, so now we need to use that solve banded import that we had gotten at the beginning. So we're going to go from t from 1 to colon. It's going to be equal to our solve banded function. And that is going to be from 1, 1, and then A and B. Okay. Looks good. Alright. So now we're going to have to plot it and make sure that it's every 5 minutes, because that's what the problem wants. So if we're going to do that, we're going to need an if statement. So if our I, we need percent 300, so that's the remainder function, is equal to 0, because our 300 represents the 5 minutes, then we're going to do a fig add underscore scatter. We're going to put a plot there. X equals X, Y equals T, and then our mode is going to be equal to lines. And then the name is going to be equal to F I. Okay. That looks to be about it. Now we just basically need to do our fig show function to show the plot. And I believe that's everything. I'm going to run back through really quick to make sure it looks right. Okay, let's go ahead and run on and see how it turns out. Alright, so we have an invalid syntax on line 24 for I in range 1, 2, and t plus 1. Okay, it looks like I'm missing a colon there. I think that's what it's saying. Let's try that. Alright, we're indentation error, expected indentation block. Okay, so it looks like the problem is that these need to be indented. So in doing so, when these are indented, this if statement will also need to be indented in order to stay within the for loop, and then this one will have to be indented as well. So I think that's what the problem was. So let's go ahead and run that and see how that works. Alright, looks like we got our plot. This basically shows the temperature changes in accordance to the time and placement on the bar from the left boundary to the right boundary. So this looks right, and this is the end of part 2 to exam 3.